Greetings, it's Shannon Mapchick Myers coming at you live from beautiful Southern California. So today is kind of a central limit theorem part 2. Last time we talked about how we can use the central limit theorem on distributions that are not necessarily normal. Their sample means will have a normal distribution with the same mean as their original distribution, but the standard deviation for the distribution of sample means is the original standard deviation divided by the square root of n, where n is the sample size of each of those individual samples that you took to find the sample means. That's a lot for a Sunday morning. I'm actually up bright and early at like 6:35 on a Sunday in the morning. So doing pretty well. Okay, so now this is what I did to illustrate how we can use the standard normal distribution to approximate the binomial distribution. So I don't know if you remember, if I can go over here, the binomial distribution, it can be a little bit grumpy. As you may have noticed before, the binomial model here, the way you would find a specific probability over n trials. So in this case, we've modeled flipping a fair coin 21 times, and the success is defined as getting a tail, right? So this portion of it tells you the number of ways you can get that many tails. So if I want to know the number of ways I can get 0 tails in 21 trials, there's really only one way that can happen, right? So long story short, if we're working with this a lot, we would use a computer program. Unless you're a math nerd like me, then you kind of love this formula. But recall that the mean of a binomial distribution is NP. So that would be the mean number of tails in 21 tosses. And the standard deviation of the binomial distribution is the square root of the number of trials times the probability of success times the probability of failure. And recall that Q is just 1 minus P using the complement, because you either have a success or a failure. All right, so that's just a reminder of the binomial model. All right, now this is what I did. There are different thoughts about how many trials that one needs in order to have a good approximation using the standard normal distribution for the binomial distribution. So I've read a couple different things, and I actually initially just ran 11 trials since the probability of success. So here, do you see that the probability of getting a tail, right, on each trial is 0.5, 1/2. And that's also equal to the probability of getting a head on a single toss. So this right here on the left side is actually equal to P, and this right here is our Q. All right. Now, when I tried using 11 trials, 11 coin tosses, it was okay, right? But it just didn't work out too well. And in some textbooks, I've seen that as long as n times p is greater than 5 and n times q is greater than 5, you can use it. But, I think that would only work if you already have symmetry in your data. So my advice is the conditions to use the standard normal All right, so let me write this out. So the conditions for using the standard normal distribution. Actually, it doesn't even need to be standardized. I'm just going to say the normal distribution to approximate the binomial distribution is, I'm thinking that n times p should be greater than 10, and n times q should also be greater than 10. All right? That's how we're going to deal with it in our class, so just keep that in mind. Cool, cool? All right, so here we go. Let's take a look. I'm sorry to throw a bunch of numbers at you again, but I think you'll enjoy just checking it out. So the very first column, binomial probability, that the probability x equals x. So on this first column right here, right, that's actually just the number of successes, right? And we've defined the number of successes, that we've defined success as flipping a coin and getting a result of tail, all right? So you can see we have 21 trials. So this is telling us right here that our n is equal to 21 because each toss of the coin is a trial. And we've listed all the possibilities here. And the only time there's only one way that you can have something happen is if you get 0 tails or if you get 21 tails, all right? Otherwise, remember, we take care of it with this portion right here, right? The n choose x. So you're basically saying, I have from 21, how many combinations are there that I can choose x? Or if you wanted to find out if for a probability that you got 8 tails, you would be, this n choose x part would be, how many ways can I choose 8 tails from 21 tosses, right? And don't worry, we're not listing that sample space. All right, so here we go. Coming back over here to our table. So the one that we were looking at down there, right, is this column. So the probability of over 21 tosses of getting 0 tails is super small. When you see this E -7, it means move the decimal to the left by 7 places. So this is really effectively 0, okay? And if you take a look at the next column, all right, the next column provides our cumulative probability distribution. So we've worked a little bit with this stuff, but when we were doing probability density functions, we just did the first table that I circled in black here. And so we looked at all of those, and then we said, oh, the sum of all these, right, probabilities has to equal to, the sum of all of these probabilities in this column, because it's a probability density function. So the summation of all the probabilities for x equal to x has to be 1. And this is illustrated in the next column because it gives you cumulative. So it adds each successive probability to the one before, all right? And as you notice, we end up getting a sum of 1. So all is good. All right, so now the next column is, what if I want to check things out and I want to get a z-score, right? Because there's a little trick to using the central limit theorem and using the normal distribution to approximate the binomial. Each of these probabilities is the probability of getting, X successes, right, out of 21 trials in the one we circled in black, the second column. Now, the cumulative probability, so these first 4, say, are the probability that X is less than or equal to 3, all right? So that means you get at most 3 successes. So here, this 0.00074488196 is that cumulative probability, and that's nice, right? Because it takes care of it for us, all right? But here, remember the Z table, right? The standard normal basically gives us, for a standard normal, this gives us the probability that some Z1 is less than Z, right? Notice there's no or equal sign. So we'll come back to that later. Let's look at a couple of problems and check it out. So the first couple problems we'll do, the first one we'll do, I think, is exact, all right? So here we go. Suppose we're interested in finding out the probability of getting exactly 8 tails over these 21 tosses of the coin. So this one is relatively straightforward. We want to find out the probability that X is equal to 8. So out of the 21 tosses, what is the probability that we would get 8 tails, all right? So this one, it'll be an approximate. We come back to our chart. The probability that X equals 8 is right here, okay? So that's just the case where we get 8 tails. So there's many different ways that you can get 8 tails, and this probability sums them all up. So here we go. Let's just go to 4. So 0.0970 would be our rounded amount. And we're all done with that one. In this next case, let me do it a different color. So in this next case, we already have the probability that X equals 8, but wouldn't 7 work? And 6, and 5, and 4, and 3, and 2, and 1, and 0 tails, right? So, hey, why don't we go over to that cumulative probability, because that cumulative probability adds up all of those possibilities. So instead of saying, oh, that's going to be the probability X is 0 plus the probability X is 1 plus ... probability X is 8. That this way we have it all set up. Groovy? All right, so let's do it. The probability that we get at most 8 tails is equivalent to the probability that X is less than or equal to X. And again, we're using the actual binomial distribution for these. So just to give you an idea and gratitude about what we don't have to do, I'll just write it out real quick. Aren't you so glad we don't need to do that? So here, using our cumulative probability, we just go right here and we find out that this is approximately 0.1917. And on this one, we used Groovy? All right, so now let's check out what we're looking for next. So here, got this value, and that was this one here for the first problem. All right, so now let's check things out, okay? Because our next task is to find the probability of getting between 8 and 12 tails, inclusive, over the 21 tosses of the coin. So again, let's go ahead and use our binomial, the cumulative binomial column, okay? And remember, this column is specific. This table, all these values are specific for n equal to 21. Unfortunately, with your probability, your binomial probability, it's not like standardized z-scores, right? Where you can reuse the same table as long as you standardize. With the binomial, what happens is you would have a total different distribution depending on how many trials that you have. So if I up this to n equals 30, I'd have to redo the whole table. Actually, let's check out our standard normal stuff. So with this one, we just found out the probability that x is less than or equal to 8 successes, right? But do you see, if you go over here, so I did all of the work for us. This column here represents the z-score that would correspond to a score of x equal to 8. And then, of course, the area here, the area for that z-score would be here. That's a bit of a problem, is it not? Because we know the answer is the pink one that's circled, 0.1917 approximately. And look, even if we said, oh, let's look at the probability that, our standardized score, we'll use 9 to standardize. Let's check that out. But look, you would still get 0.25. It would not be right, okay? Now, let's examine the reason for that. So here, I went ahead, I don't know if it's just me, but they don't make the bars touch. I played around with it, couldn't make it happen. So I just did the tops of where the bars would be. And look at that. It really gives you, do you see, it really looks like a very nice normal curve, doesn't it? I mean, if you drew that in, you would have quite a bit of symmetry, right? So, but what happens in reality with each of these little bars, okay, it is that, and this is the model of your density function here, okay? And you've got things that are effectively, so you see you have things that are effectively 0, right? And so what happens here is that you've got all of these bars, right? But what are they landing on? They're landing where the middle of that bar is your number of tosses, of successes, right? Do you see what's going on here? So, how can I change that? Because, and you could keep going on. I'm sure you don't want to watch me make all these bars that represent the probability density, but this would be like 6, 7, 8, 9, etc. And so what's happening here, right, is that these bars, are they really going from our exact numbers, like less than or equal to 8 tosses, or are they offset a little bit? Beautiful. They're offset, aren't they? They're offset by a half each way. So if you think about it, this here is really negative 0.5. This here is positive 0.5. And so the probability of getting exactly 0 tosses is really bound between this interval between negative 0.5 to positive 0.5, etc. So just examining another one, when you're looking at 6, well, we'll do 5 right here. 6, I think I kind of got a little offset on those. But let's look at 5. Do you see 5 is really going from 4.5 to 5.5? Cool so far? And think about it, it makes sense because what we're doing is we're going from a discrete probability density function or distribution to a continuous probability density function or distribution. So there's an easy fix. What do you think we would do? Beautiful. We would add 0.5 to each of our z-scores. So here, if we take a look at these probabilities, okay, using the standard normal, we realize that that's just not going to work because that would assume that all of these bars were shifted either to the left or right by 0.5. So let's check it out. Let's go ahead and look at this continuity correction, right? This is called a continuous continuity correction. And so that's for the z-score. So I just added 0.5. Now the 10.5 comes from the fact that, remember we figured out the mean. So we had said the mean was equal to NP. And so 10.5 is actually equal to 21 times 0.5. Okay, so NP. So we're adding 0.5 to each individual x value. Remember, the x means number of tails. And then we're standardizing it by dividing by, and then we subtract from our mean. And then we're dividing that by the square root of n times p times q, which is our standard deviation. And so now we've got this change, and look what happens. All right. So remember, we were interested way back when, because you know me, I have to talk too much. We were interested in the probability that x was less than or equal to 8. And that is where we were able to find this one here, the 0.1917 approximately. Well, check it out. Now that we did our continuity correction, 8's going to be included. So here, right, let's go and figure out where 8 went. This would have been 5.5. This would have been 6. This would have been 7. This would have been 8. And so what we've done is we are basically going from 8.5 for our x. So we're finding out in the z table, or just in the standard normal, the probability that x is less than 8.5 as an approximation with that continuity correction, right? And then lo and behold, what did we find out? We found out that, dun dun dun, we end up getting, what color am I doing for this? I'll do the orange. We end up getting the 0.1913, which is pretty close. We're what? About, or 0.1914. So we're about 3/10,000ths off. Okay? Here's a better picture here because the 0 is up a little bit. So I shaded in the area under the curve for the bars that I drew from that. So using our continuity correction, we can use the standard normal to approximate the binomial distribution as long as n times p is greater than 10 and n times q is greater than 10. Groovy? Okay, so let's do the other problem both ways. So we already know this lower amount because isn't this probability of getting between something, wouldn't this be the probability that 8 is less than or equal to x is less than or equal to 12? So we want to find out if you get the probability of getting 8 tails or 9 tails or 10 tails or 11 tails or 12 tails, right? So if we use our binomial distribution, right, that would end up giving us what? The probability that x was less than or equal to 12 minus the probability that x was less than or equal to 8. Good so far? Well, we already found the second one, didn't we? We already found that to be 0.1917 in the second item of this example, which, by the way, well, this is part 2. I mean, I guess this is sort of example 2 still. So here we go. This is 0.1917. Already found it once. Don't need to find it again. And then let's now find the other one. So the other one, I'll do in the darker purple, I guess. Well, no, I did that in something else already. So the other one we shall do in this purple. So if I go here on my chart to my cumulative probability, do you see that I get 0.8083 approximately? Good so far? And remember, that gives me all of this, all of those, whoops, all of these possibilities, okay? And they're added all up. So 0.8083, and now if we find the difference between those, let's see what we get. We get this is equal to, you know, I'm tired, so I'm going to go ahead and do it on the calculator. So here we go. All right, so doing it on the calculator, I got 0.6166, okay? And that's the probability of getting between 8 and 12 tails inclusive, so you're including those endpoints, over 21 tosses of the die. And this was using our cumulative binomial column. All right. So now let's check out what would happen if we used our standard normal. All right. So our standard normal is finding a different probability, is it not? So this one, using the standard normal, say approximating with standard normal, and using our chart, because we already have that, right? That's going to be the probability that X is between 12.5 and 8.5. Good so far? And then that in turn is equal to the probability that X is less than 12.5 minus the probability that X is less than 8.5. Now we standardize these scores, right? And so when I standardized them, I got for the 8, using the continuity correction, I got approximately negative 0.87, and then so we have negative 0.87 and negative 0.19. And then the other one was, or no, that was the associated area. The other z-score in turn was approximately 0.87, right? And I'm getting that from I'm running out of colors. Here we go. So positive 0.87. Remember, we round to the nearest hundredth if we're using a table. So, and then we're subtracting these. And now we'll just go ahead and use our table. And on our table, what do we have? The associated probability with this one using standard normal is, I'll go to 4 digits on the probability, 0.8086. And we'll subtract from that this other probability. And that other probability we had already found right over here, or we had looked at, and that is 1914, sorry. And when you get your end result, this is what we'll have. We'll have 0.6172. So not bad, huh? It's just, 6/10,000ths away from what you got with the actual normal distribution. Good so far? All right, so anyway, that is the lesson today, and I hope you have a fabulous day, and I will talk to you soon. Bye.